That desk is for a field student that Mr. Chamberlain has this semester. So, okay, page 68. We've got we're going to crank through this week. We're going to wrap up all the limits so that we can do derivatives starting next week, Monday. So, let's go at it. These are the questions that you guys had from page 68 that I want to go through. So they were all pretty good problems to go through. So let's go do it. Okay. First question was number 76. Did that look familiar? If you check your notes, I did that problem in class. And so you might want to look back on that. I'm not going to do it again, but what we did was we converted the tangents to sine over cosine and then cleaned it up, did some canceling, and then you can substitute. So that's number 76. All right, number 78, let's go ahead and do this. So this whole thing is about algebra and rewriting. So I'm going to try to rewrite this bugger. Limit as x approaches 0. What I do see is the sine of 2x over the sine of 3x. Now, can I pull out the 2 and the 3? I guess my question is this. If I have the sine of 2x, is that the same as 2 sine of x? Is that legal? Because I've seen people do that. So it must be true. Is this the same as this? Okay, people who are saying no, raise your hand. I need justification. Why not? Why are those not equal? What in your past have you learned, Tim? Okay, here it's doubling the x. Here it's doubling the whole sine of 2x. Okay, mathematically, I can get that. Can you picture what this one looks like compared to what this one looks like? What does the number in the front do to the graph of the sine? Increases the amplitude. Okay, it's twice as high as it was before. You may remember what the 2 does? It shrinks it. Instead of being one period, one full cycle in 2 pi, you have 2 full cycles within 2 pi. Okay? This tells you how many of the cycles you have in the length of 2 pi. So this is certainly not true, which means I can't just pull those out. So let's do a little algebra then. So I don't know, I'm going to say sine of 2x times 1 over 1 times sine of 3x. See what I did there? Don't be afraid to write stuff out and just try something. Worst case scenario is you just stare at it. Okay? Kind of doesn't get you anywhere. So, not that anybody here has just stared at a problem. But, okay, so when you need an x, you just put an x in there. Just do it. Okay? Well, and as long as we compensate for it, then we're not having a problem here. So that's fine. I'm multiplying by 1. So this guy needs a 2, so put a 2 in there. Compensate it by putting a 2 up above. Now again, we're just rewriting it in a form that makes it, that allows us to do the limit. By adding a 3 on the top, 3 on the bottom, now I can go ahead, and if you look closely, what you'll see is this, I'll do the whole write out here. Limit as x approaches 0. This is really of 2 times the sine of 2x over 2x times 1/3 times 3x over the sine of 3x. You see that? You got to be able to see how what we were really doing here in order to make this work. Okay? And this becomes 2 times 1 times 1/3 times 1. And would you look at that, the answer is 2/3. The 1/3. This one needed a 3 and a 3 to match the 3x. So I kept the 3x on the top here. And this 3, it was this 3 that turned into the 1/3. Good? Okay, so be able to handle any problem like that. This is one of those cases where if this was a multiple choice and all you'd said was, well, just take the 2 out and take the 3 out, you would get the answer right by accident. Okay, it's not the reason why it is what it is, but that's the deal there. On a problem set, if you put an answer, like you got a problem set due tomorrow, if you give me just an answer, okay, then you get it right, you get 1 point for that out of the 5 points for each problem. But you got to show me all the work to get there. No.
Wasn't one of your best.
It wasn't intended to be one.
Pretty good circle. It's Monday.
It's a row. Greek letter row. Okay. All right. So next problem, 83 says find the limit as delta x approaches 0 of this big blob if f of x is equal to 2x plus 3. Okay. So let's go do it. So to find the limit, we just start right at it. Limit as delta x approaches 0 of. First thing it says is to find f of x plus delta x. Okay, if this is f of x, then f of x plus delta x says just take an x plus delta x and stick it in for x. So this first part right here turns into 2 times x plus delta x plus 3. See it? Okay. All I did was take x plus delta x and I stuck it in for x and I got that. Okay, minus f of x. Well, f of x is 2x plus 3. So it's minus 2x plus 3. And this whole thing is over delta x. So then we just have to figure out the limit. Looks kind of ugly on the top, so let's clean it. So I'm going to just do a little distributing and see what we get here. What do I got? 2x plus 2 delta x plus 3 minus 2x minus 3 all over delta x. Anything cancel? Yeah, positive 2x, negative 2x. Positive 3, negative 3. So the only thing I'm left with is 2 delta x on the top. So this whole thing becomes the limit as delta x approaches 0 of 2 delta x over delta x. Can I plug the delta x in? No, I get 0 over 0, which we know as indeterminate form. So, but delta x over delta x, hey, that's 1. Okay, so the limit here is as delta x approaches 0 of 2. That's all we have to figure out. What is the limit as delta x approaches 0 of 2? 2. Delta x can actually approach anything it wants to on this problem, and the answer is still going to be 2 because this is the function y equals 2. It's a horizontal line, and the limit as you approach anything will always be 2. What we just did there was we found the derivative of a function. Okay, so here's the point. If f of x is equal to 2x plus 3, then this limit is the derivative, which is called f prime of x, and it is equal to 2. Okay, the derivative is 2 if the function is this, and we're going to expand our knowledge on that more later, but this was just finding the limit. So far so good? Okie doke. Next one. Use the squeeze theorem to find the limit as x approaches 0 of f of x if f of x is in between 4 minus x squared and 4 plus x squared. So, bottom line it. What is the limit as x approaches 0 of f of x? That's what I want to know. What I do know is that f of x is greater than or equal to all the values of this and less than or equal to all the values of that. So it's in between. I'm just going to do a quick graph. I want to see what this looks like. So 4 plus x squared, graph of that. 1, 2, 3, 4, that's a parabola that looks like that. 4 minus x squared, that's the parabola that looks like this. And f of x has to be in between there. So for each of these values, whatever the x is, so this has to do something like this, whatever. F of x has to be in between those two. That's what that double inequality means. So what is the limit? Look at that picture. What is the limit as x approaches 0 of f of x? It's 4. It has no choice, right? It's just sort of squeezed right in between those two. So the answer is 4. Yeah. Mm-hmm. You're graphing it to validate that it's going to get squeezed. Yeah, if you want to plug things in just to validate it, to make sure. Okay. Yeah, plug a 0 in here, plug a 0. They're continuous, so we can find that the limit of each of those is going to be 4. So that thing the limit has to be 4 on that one.
Okay, but it has to be continuous for you.
Because that's that whole thing, otherwise you can't plug it in. Okay. What is meant by determinant form? Well, we know that. That's like 0 over 0, but there's more than that. Okay? So add this to your list. Sometimes if you were to get like infinity over infinity, okay, you just can't determine what that is. It's indeterminate. Okay? And then other combinations. Infinity over 0. What's 0 divided by infinity? Okay? Those are just really, they're beyond weird. Okay? They're extraordinary, and they get labeled as indeterminate. I'm going to teach you a special little rule later on. It's got a great story behind it, but you need to know what an indeterminate form is in order to do it. It's a way to figure out a limit by using the derivative. Yeah.
Would 0 divided by infinity not just be 0? Because 0 divided by infinity.
Yeah, it's got a point there. The only problem is infinity is not a number, so we can't quite do it. So, good thought though. All right, 17 was a true, or 117 was a true false. The limit as x approaches 2 of f of x is equal to 3, where f of x is equal to 3 when x is less than or equal to 2, and 0 when x is greater than 2. Is this a true or false statement? I'm thinking false as well. So what do? You graph it. Okay? So x equals 2 here, and this thing says we graph x equals, or y equals 3. Y equals 3 when x is greater than or equal to 2. So that's this one. And then x is equal to 0, or y is equal to 0 for all values when x is less than 2. Oh, I got those backwards. Thank you. X is less than or equal to, or this way, and greater than or equal to 2 for this way. Do you agree that that picture matches the function? Okay. So with that in mind, is the limit as x approaches 2 of f of x equal to 3? No. What is the limit? Does not exist. Okay? And we've talked about left-hand limit and right-hand limits, which is the next section, which is really going to be an easy transition for us. Okay, and finally, number 119 says find f such that the limit as x approaches c of the absolute value of f of x is equal to the absolute value of L. However, the limit as x approaches c of f of x does not exist. So we have to come up with a graph that matches that somehow. So how is that possible? So x is approaching some c. I don't know what the c is, but it's somewhere there. And the limit as x approaches c, now the absolute value, that's going to be kind of the clinker here. I'm going to try something. Okay, let's pretend this is my f of x. Okay, and this is some number L, and then this is at negative L. It's the opposite of whatever L is. So I'm going to start with the backside. Does the limit as x approaches c of f of x, does that not exist? Is that correct? This does not exist. That limit does not exist. But if I take the absolute value of f of x, does it equal the absolute value of the limit? What that means is it takes whatever negative numbers were negative, it makes them positive. So it takes this, and it makes this graph positive. So this is the graph of the absolute value of the original one. Made everybody positive. So this limit does exist. However, the original function did not exist. The limit did not exist. So a graph that looked like here and there, just like we had there, would satisfy it, as long as we were symmetrical over the x-axis. Okay. Hey, by the way, homework questions or questions in general, if you have any questions, remember that my room is B215. It's the computer science lab. So I'm in there after school every single day, just lonely, twiddling my thumbs. So if you have any questions, I would be more than happy to go over things with you. So keep that in mind. All right, we'll open up your notebook to the next section, or to where we were. We're going to continue on where we were. We're going to learn another rule today. We're in 1.4 talking about continuity. All right, I want you to copy down this formula. It's called the intermediate value theorem. We're going to copy down the first half, and then you're going to fill in the blanks. So here's the rule. If f is continuous on the closed interval from A to B, and k is any number between f of A and f of B, then there is at least one number C in the interval, closed interval from A to B, such that fill in the blank. Read it and figure out what goes next. And then be able to justify it. Read it, figure out what okay, if f is continuous on the closed interval A to B and k is any number between f of A and f of B, then there is at least one number C in the interval A to B such that what? Such that what? Draw a picture of this. Draw a picture of this. This is part of our technical reading and technical writing. Draw a picture of what this looks like. Everybody a little sluggish today? No particular reason. Okay, draw a picture. So I'm going to draw a picture. See what I got here. This is what you have to learn how to do, formulate this thing. So f is a continuous function on a closed interval from A to B. So I'm going to slap an A over here, slap a B over here. Okay, and this is including, sometimes you see this notation, it means it's a closed interval, which means we can use the A and the B. So, and k is any number between f of A and f of B. Well, that's weird. I thought I was supposed to say A and B. So, a continuous function. So, I'll just make this thing up here. This is my f of x function. So watch this. If I put A in, what I get is a y value, which is f of a. And if I plug a b in, I get a y value, which is f of b. Okay? F function, that's f of a, that's f of b. Those are the y coordinates. They call them the functional values. So according to this, it says, and k is some number between f of a and f of b. So I'll just put a k in there. So this picture matches everything that I've underlined. That's what that means in a picture form. And that's what the skill that you're going to have to develop. Then there is at least one number called c, in the interval from a to b, such that, Kendra? F of c equals k is correct. Anybody else be thinking that? Okay, phew. So the correct answer here is that f of c equals k. Looks like you got to be careful writing that one out. Okay, so let's see. On my picture, this is where C would be located. Okay? If I said, oh, I'm going to choose my K here, if I did that, then my C, corresponding C, could be here, or it could be here, or it could be here. Because it says, then there is at least one number, which means you can have more than one. In other words, if you've got an open interval, the key is that the function is continuous. If it's not continuous, this whole thing blows up, and it doesn't work. As long as f is continuous, then there has to be a value that if you choose a y value here, there has to be a corresponding x value here. Has to work every single time. In other words, if you picked a value that was intermediate, was in between these two, then you have to get one that's over here. It's got a comb over. Okay, so let's answer the question on the board. Is any real number 1 less than its cube? Is any real number? All I want is a yes or a no. I don't need to find what it is. I just need a yes or a no. And then I need justification why. You knew it wasn't going to end there. Is any real number 1 less than its cube? What does that mean anyway? Is any real number 1 less than its cube? Like 3. 3 is a bad number because it's got the cube. 2. 2. According to this, does 2 satisfy this? 2 cubed is 8. Is it equal to 7? 7 is 1 less than the cube. So I want to know if you take a number and you cubed it and then you subtracted 1, can you get the same answer you started with? Is that possible? Seems like the bigger you get, the worse it gets, right? 4 cubed, 4 times 4, 16 times 4. Do you guys know how to multiply by 4? Really easy. You double a number and then you double it again. So 16 times 4, you double 16, you get 32, and then you double 32, you get 64. So we know that. So you take away 1, you get 63, and 4 is not equal to 63. That doesn't work. And it gets worse as you go higher, right? So is it possible? Does there exist a number such that if you cubed it, you subtracted 1, it's the same as the number you started with? Well, I wonder if we can use the intermediate value theorem to prove it. Okay, so using the intermediate value theorem, let's create a function. What is the function that corresponds to this? What is a real number? I'm thinking of this. Y equals x cubed minus 1. You take a number, cube it, you get 1. Maybe I should use f of x here rather than y. And then the x would equal to f of x. That's the goal. Okay? So this function matches this. Remember how I taught you multiple perspectives? What is the graph of this thing? Y equals x cubed minus 1. It's this guy, but shifted down 1. Okay, so it looks something like this. This is the graph of that. The answer is staring you right in the face. Yes. -1. -1 cubed is -1 minus 1 gives you -2. I should say we're close. This is the graph of x cubed minus 1. Okay? If you plug this in here, if you found this answer right here, okay, it would be, it's right at +1. The question is, how can we use this and this together? Well, let me propose this. Don't we really want this? See what I'm saying there? If we could find a number such that if you cubed it, you subtracted 1 from it, you got the same number, we'd have our answer. Okay? Pull out your calculator, graph that, and we'll put a sketch up here, and we'll see how this relates to the intermediate value theorem. Ooh, how do I graph that? So one solution, and this is where you get to begin to have a choice here. You can make one solution is to graph both of them. Okay. So that's one possibility. And then where's the answer? At the intersection. Okay. What's an alternative way to do the problem? Because that's not the only way to do it. Don't need parametric. This is one way to solve this kind of problem. Sure. Set it equal to 0. So I'm going to say 0 equals x cubed minus x minus 1. And I'm going to let that one be my equation. I should write it like this first. You get your 0, and then from there you type it, and then where's the answer on this one? It's the x-intercept, so it's a root. Okay, this is where you do the intersection. This is where you do the root. So I'm going to graph this. We're going to do this one. And do a zoom 6 so we all got the same thing. So I'm going to do another little zoom box. Take a peek at this. I'm going to only look at this part. Okay, what we have here is a continuous function. It's x cubed minus x minus 1. We know that if it's equal to a negative number, we know that it's not a solution. If it's a positive number, it's not a solution. It has to be equal to 0. So in this case, the k value is 0, and the c value is whatever the root is. So this is where the answer is. So I'm going to teach you something that you may not know, but you gotta know. Hi, Harry. You brought me a cookie. You're awesome. Perfect. Save that for later. So let's do find the root. Okay, so let's do that. So we're going to do second calc. And then go down to 0. Do your left bound, so you have to just be somewhere to the left of that x value. It doesn't matter where you are, just to the left. And then you have to go to the right of it, and it doesn't matter how far you go. And then you have to guess somewhere in between. You don't have to guess right on it. So there's an answer of 1.324718. So x is equal to this. Did everybody get that? Okay. How do we test to see if that answer works? I want to take the cube of it. So did you write it down? Okay, so watch this. So I'll clear this out. And so you might write it down and you say, okay, 1.324718. I'm going to raise it to the third power and subtract 1 from it. Oopsie. Minus 1. Well, this has got a little garbage on the end here. Did you get garbage? Okay. So that answer might not be rational. Okay. So how do we get the exact value out of here? Okay. Let me show you something cool. Go to the graph, y equals, or you go to the, oopsie, hey. I got to put my graph back in here. X to the third minus x minus 1. And do this. Calculate the 0 again. Second calc. Go to 0. Just like you did before. Technically, if you did it already, it's still there. So left bound, right bound, and then get inside there. Now, once you get it, just press second quit, and press X. The calculator has an extremely good short-term memory. If you look for a 0 or an intersection, now you can take it and you can cube it, and then you can subtract 1 from it, and it's the same value as x. We'll touch more on this a little bit later. All right, homework this week. Problem set due tomorrow. Page 78 due tomorrow. 88 due Wednesday. 205 due Thursday. It's a good homework week. Yep. 3.